Good morning, everyone. Can you hear me okay? Right. I just want to thank the organizing committee. It's my first time at Leeds. It's really nice to be here. Especially Veronica, it takes an incredibly organized person to organize a disorganized one. So thank you for that. Today I'm going to be talking about Saffman-Taylor instabilities and shear-thinning fluids. It is based on work that I did write a paper on that's recently been published as a sole author. However, I really do need to thank my collaborators for their discussions, which have always been very useful. Rebecca Mather is actually only a third-year student at Manchester University, but she is absolutely excellent. Many of you will know Michael Gray-Worcester from Cambridge University, who I have worked with before. Nicholas Hale is actually all the way in South Africa from Stellenbosch University, who's my go-to numerics person. And Thomasina Ball, who is a lecturer at Warwick University. So it really is, thanks to these people for keeping me on the straight and narrow and hopefully presenting work that is interesting and, of course, makes sense. So I'm going to start off very simply. I know that a lot of people in the audience perhaps also work in turbulent flows and high Reynolds numbers. So just in case, anyone's forgotten about what happens at low Reynolds numbers, just going to explain what we're looking at in this talk very briefly. So we're looking at things that are called Saffman-Taylor instabilities, which are these finger-like instabilities that occur when you have a less viscous fluid intruding into a more viscous one. So the type of setup that we can look at here, I like to look at what's called a Hele-Shaw cell. So we've just got two parallel plates where our fluids are confined to those. Or you can even look at porous media flows. But I really find the Hele-Shaw flows quite messy experimentally, so I haven't quite ventured into porous media flows just yet. So how does this actually all work? Well, if we have a less viscous fluid that's intruding into something that's more viscous, a lower pressure gradient drives that flow, whereas a higher pressure gradient is needed to drive the flow of the more viscous fluid. So what happens is, if we have any interfacial instabilities that allow some of the less viscous fluid to intrude into the more viscous one, those little disturbances are now in an environment with a higher pressure gradient, but because they're less viscous, they're more mobile than the surrounding viscous fluid, so we actually get these extended fingers developing. Now, Saffman-Taylor instabilities have been studied thoroughly in the literature, but I'm actually always a fan of revisiting problems to see if anything, interesting comes up, something new and exciting, and that is actually what I found. So often there are some, gaps that hopefully will be of interest, and worthwhile to pursue. Anyway, I find it very interesting. So this is, you might probably look at this and see the most amateur-looking experiments ever. I'm not an experimentalist, but I am a mathematical modeler, and I like to know at the end of the day if my models actually represent reality in at least, vaguely, because it helps to guide my mathematical models to introduce further assumptions, or perhaps sometimes even going down the wrong way. So here is an experiment where this clear liquid, that's silicone oil, it's very viscous. It's got about a viscosity of 1,000 times greater than water, so that just gives you an idea. This blue little circle here, maybe quite hard to see, that's xanthan gum. It's a shear-thinning fluid. I'll explain more about its properties later and why it's important that it's shear-thinning in this case as opposed to not another Newtonian fluid. In all of these experiments, I'll explain how we get this initial radius, but we start off with an initial circular profile. So we don't just start off with r equal to 0, basically. We start off with a really small circle. And that's something that we can vary from one experiment to the next. So why would this be, I guess, more interesting than the case if we had just two Newtonian fluids? Well, with the xanthan gum, its viscosity increases with radial distance. So what I hope to see when doing these experiments is that I would see some Saffman-Taylor fingers, but I expected that at later times, the flow would actually return to its axisymmetric configuration. And that is because the viscosity of the shear-thinning fluid is increasing. So eventually it will get to a state where its viscosity is greater than that of the surrounding fluid, and conditions favorable for Saffman-Taylor instabilities would not be met. So that's what I hoped, and This is what one of the experiments showed. So it's not super dramatic, but I thought it was still a really nice experiment. We could clearly see at early times that we had our interface, those perturbations developed, and they did indeed grow. But at later times, you can see that it's starting to return back to a circle. And then I think the camera actually drops soon. So when I say these were very much done by an amateur, I wasn't joking. But this is really just to get an idea of what's going on. Okay, so I'm just going to make the experimental setup just very clear before I move on, otherwise the talk might not be as interesting afterwards. So we're looking at a setup where we've got two parallel plates. In the lab I just had, In the lab I just had two glass plates, which they might have been better materials to use, but we'll get to that shortly. So what we do is we actually start the experiment with the top plate removed, and just a blank glass sheet that's got a hole in the center through which we can pump our xanthan gum. So what we do is we pump a little bit of xanthan gum onto the bottom sheet, however much we want to get the source radius that we require. I mean, this really does sound amateurish, even as I'm saying it out loud. So then we pour the silicone oil carefully around the sides of the xanthan gum, and you really gently lower that top plate and then clamp it on each corner to make sure that everything's secure. But you do actually get quite a nice circular profile, in most of the experiments at least. But I found that when my students did it, they were way more patient than me, so their results were better. But, there is definitely a better way to do this. I just need to first gain some confidence in the actual experimental setup before proceeding with the whole suite of experiments. But basically, again, the whole interesting thing about this is this shear-thinning fluid and the viscosity depending on the radial distance. So that's what gives rise to some cool new features that I, well, at least hope to convince you are actually quite interesting. So in all the experiments where we did see instabilities, there were actually some where we didn't, and I'll explain why shortly. We started off with something circular, well, as circular as we could get it. Even that in itself is an interesting problem, to see what that initial profile, what impact that would have on the perturbations as well. So theoretically, that would also be an interesting problem, which I haven't addressed. Anyway, we hope for the best, that we're starting off with something circular. As time goes on and we pump in xanthan gum, we start to see these fingers forming, and then eventually it goes back to an almost circular profile. But somewhere in between these states, there is a time at which we would expect the system to be at its max asymmetry, in a sense. And you can actually determine that point. I haven't showed it, but if you calculate the perimeter of the interface and you divide that by the perimeter of the circle that would have been were the flow symmetric, then you can actually get an indication of how asymmetric the situation is. And it is quite nice. You see a nice peak, and then it tapers off, showing that it becomes a circle again. Okay, so there were some experimental findings. Not, like I said, I didn't do a huge number of experiments. This project actually started off with the mathematical model. I'm doing it the other way around. I think I was hoping to generate more interest than showing 100 equations first. So on this side over here in these panels, these are just some images from some of the experiments that were done. Now everything was kept the same. So we had the same xanthan gum solution, same silicone oil, viscosity, everything was the same except for the initial injection radius. So at the top one and the second one here, the initial injection radius was quite small, and here it was much larger. So you can see, first of all, that it appears that there are small mode disturbances, at least featured in the top two experiments. But if you look at these, I mean, the instabilities are not really that pronounced, and it seems like, if we look at sinusoidal disturbances, we're more looking at low wavelength disturbances in this case. So this is great, but my goal is to compare this to a mathematical model that I've developed. Now, when it comes to comparing theory and experiments, again, I like to take the path of least resistance and think about the simplest thing that I can compare. And the simplest thing that I can compare is the initial injection radius and the fact that the experiment showed that there was this critical radius, that if I chose an initial injection radius greater than this critical radius, I actually didn't get any instabilities. So basically, I've got this critical radius. If I start with something less than that critical, I see fingers forming. But if I start with something greater than that critical, I don't get those fingers forming. And that's a result of the viscosity of the shear thinning fluid being greater than that of the surrounding silicone oil. So I've got this criteria that will determine stability. And it also appears that we have an increasing series of critical injection radii for each mode disturbance. So this was just what we kind of learned from the experiments, but I'm hoping to put it all together a bit more neatly now when I look at the theory. But again, that is the easiest way. Do I get instabilities or don't I? Instead of doing all kinds of fancy measurements, experimental measurements, which I'd like to at some stage, if we can't get that right at the start, then there isn't much hope of other things, working out if we compare theory and experiments if one of the most basic things doesn't correspond. So for those that maybe don't really deal with shear thinning fluids, the one that I used is xanthan gum, and I don't want to sound like a free advertisement, but I found Mr. P xanthan gum was a very consistent brand to use, and you want to try and get as much consistency as possible. So after using Mr. P xanthan gum in multiple batches and all sorts of that, I was actually rather impressed by how robust the properties seem to be quite consistent. So what we have here is, we stick our xanthan gum into a device called a rheometer, and it will tell you what the shear viscosity versus the shear rates is, and this is just a log-log plot. So that looks like a nice straight line, which means that for these type of fluids, we can use a power law model to model them. So N there is the power law exponent. N greater than 1 corresponds to a shear thinning fluid, and M is the consistency index. So based on the data from the rheometer, we can easily determine those values. So that's really nice. At least when I'm modeling, I don't have to guess what those values are. I actually have some idea about what they correspond to. And again, what we're interested in is really this viscosity that depends on the radius, because as we start off with larger and larger injection radii, the viscosity of that shear thinning fluid is going to increase. Okay, so I'm not going to go through all the equations, but I'm hoping at least to give some indication of how intense it actually was to get through these. Not necessarily very difficult, but not the most exciting, time I've spent, especially when you make 1,000 mistakes. So what we do is we start off with the lubrication equation. So we're looking at low Reynolds number flows, and we can actually verify that we're in a low Reynolds number flow regime by using our experimental parameters and checking all of that. So we also assume that the gap between the two plates is really small, much smaller than the horizontal extent in which the fluid is flowing. So we've got our lubrication equations. U is the R velocity, W is the theta velocity, P is the fluid pressure. These complicated looking expressions here, that's just to model the viscosity of the shear thinning fluid. So if we had Newtonian fluids, N would just be equal to 1, and those terms would disappear. So it's quite simple for the case where we have Newtonian fluids. But if N is not equal to 1, we've got a whole lot of non-linearity introduced now, which we have to take care of. So we have to solve these subject to the no-slip boundary conditions. So I've just positioned my plates, my top and bottom plates at minus h and h. And we also have global conservation of mass. So U bar here is just the average radial velocity across the depth. That is related to the flux at which we inject the fluid. So I'm not going to solve these, but it would actually, be of interest to solve these numerically, the full set of equations at some point. But I just want to get out the most basic information possible so that I can try and compare these things to experimental results. So what I do is I'm going to perform a linear stability analysis. The first thing I do is to find the base flow solutions. There is a reason why I have to go through this. I just need to point out one or two things. So this is the case where we have our W velocity, the theta velocity is just 0. Everything is spreading out radially. So we can find our radial velocity, our viscosity, the pressure gradients, the interface, and the minimum viscosity. So far I've been talking a lot about the viscosity of the shear-thinning fluid being greater or less than that of the silicone fluid. But if you look at the viscosity, it clearly depends on the vertical coordinate Z and the radial R. So ideally, it's a little bit tricky when I say, when I compare the two viscosities, but we'll see later on that we can actually define an effective viscosity that basically is, it's not an average of the viscosity of the depth because there's infinite shear at the interface, but, did I get that? Probably not the right way around, but it's an average in a different sense. So we'll get to that. But what we need to know is just this minimum viscosity, which occurs when Z is equal to H. You're looking at the top half of the plane, so that is where the shear is the greatest. Sorry, shear goes to 0 on the center line, so yes, we have an infinite viscosity. Okay, so before, it's always good to non-dimensionalize, makes your life quite a bit easier. You can also see what groupings of parameters are important. I'm not going to go through all of this. What I just want you to remember, I guess, is that this capital S this denotes the position of the interface between the two fluids. So that is equal to the dimensionless base flow A of T, where it's just spreading as a circle, plus some perturbation zeta. We do the same for the pressure and all the velocities, and this here is the viscosity that we also need to perturb as well. So once we do a whole lot of reductions, we get to, for those of you that are familiar with the field, the expected results that the pressure solves the Laplace equation in the Newtonian fluid. But in the non-Newtonian shear-thinning fluid, we actually have a modified equation that now depends on the exponent n. So if n was equal to 1, then it would just reduce to the Laplace equation, and that is the classic problem, of the Saffman-Taylor instabilities for two Newtonian fluids. I've also got some interface conditions. So basically, what I do is I continue with my linear stability analysis, and I look at some perturbations of the form given here. And what I'm interested in is that perturbation amplitude zeta k, and whether that is going to grow or decay. That's what I'm interested in. So you take all of this, you substitute it into the boundary conditions. I think it's about 30 pages of work with some additional checks, which I checked many times, so I'm very confident on the results. So we get this expression, this equation, this evolution equation for zeta kt. So k is just the mode number. I was just looking at mode numbers from 2 to infinity. So what we really want to understand is the sign of this. If it's positive, it means that my perturbations are going to grow, but if it's negative, they're going to decay. This lambda kt has a complicated-ish expression, but what really appears in it is something which I called the effective viscosity, which is related to the minimum viscosity. And the best way I can describe it, it's almost like the Newtonian analog viscosity, but instead of, in this case, depending on Z and R, it just depends on R, which is what we want. So what I'm going to do is I'm just going to provide some plots first of these perturbation amplitudes so we can see how they behave. But then what I'm really interested in, because it is the easiest thing to compare, what happens for early times? Do I get instabilities or don't I? That's all I want to know. Sorry, I seem to be knocking this off of quite a bit. Okay, so, I mean, not much of interest here. We can just see that the lower mode numbers, they don't reach such a high amplitude, but they also decay quite slowly. Whereas with the larger mode numbers, they take longer to reach their peaks, they reach higher peaks, but they also decay rather quickly. I haven't had time to really think about this in terms of the experiments, beyond the type of mode numbers that I think we see based on the injection radius. But I guess here's where the really cool, interesting, simple expressions come out. So I want to look at early times. So I'm going to look at lambda k when t is equal to 0. And basically I want to know, when is this negative? When is it positive? And if it is negative, then that means that I can find a critical radius which determines stability. So I can do that for all modes to be stable. This is the critical radius that I obtain. So if A0 is greater or equal to that critical, I don't see any Saffman-Taylor instabilities. And then we also have a critical radius for each mode K, which is related to that critical radius for all modes. And we have this function here. Now, hopefully, as you might expect, you would expect that AK sequence to be an increasing sequence with an upper limiting value of AC. Because if you're looking at successive values of AK, and if you have an injection radius greater than AK, it means that all modes smaller than K are stable, but all modes greater than that are unstable. So as we take K going off to infinity, we expect to see AK over AC tending to a value of 1. I won't talk too much about that. Probably don't have much time, but that's just to show that we've got this increasing sequence. So the larger our injection radius, the more modes that are initially stabilized, basically. And then there's a critical radius where all of them will be stabilized. Okay, so here comes, I guess, the tricky, well, not really tricky parts, the moments of truth, where you compare your experiments and your theory. So I just want to bring your attention to the right side. Yeah, that's right side. So in these experiments which I showed earlier, you can see all the experimental parameters. Everything was kept the same except for the initial injection radius. Now, for the theoretical estimates, the main thing to look here is that value AC, which is 9.6 centimeters. So what theory told us is that for these experiments and these experimental parameters, I would only see stability of the interface for an initial injection radius greater than 9.6 centimeters. So that means that the chosen injection radii I have for all of these, which is 1.8, 1, 0.8, 0.5, I expect to see instabilities initially, without a doubt. If I had to choose something greater than 9.6, I would expect it to be stable. So with the very, I guess, bizarre methods of how these experiments were done, it's quite difficult to get a large initial injection radius. So at least with this case, we knew though that we should see instabilities. And we did, but if you look at the last experiments, they don't seem to be particularly dramatic. So we add a radius of 1.8 centimeters, that's what we start off with, and we don't see anything quite so dramatic. But theory tells us that we're still very far away from the radius that determines stability at 9.6. I mean, this is just a feeling, but it seems a little bit odd that we're looking at something that's almost stable, but we're still so far away from that. So we ran some other experiments where, one, I wanted to get more dramatic fingers because, you know, this, I mean, they're interesting, but I mean, you've got to admit this picture looks a lot nicer. So I wanted to see really dramatic fingers, so I looked at a higher viscosity silicone oil, and we did indeed get our very nice fingers. And in actual fact, in this experiment, these fingers didn't suppress as time went on. They actually pierced the silicone air interface. So that was a very interesting thing as well, to actually look at finite domain effects on these instabilities. Okay, so then in the next experiment, I wanted to get an initial injection radius that was much smaller than what was determined theoretically, but still show that there were no instabilities. Now, to the eye, that's pretty circular. Sure, depending on what you want to zoom into, but in this case, to see something of use, I would expect these instabilities to, at least be of the order of magnitude of the gap between the plates, or something like that. So that looks pretty symmetric, and there were more experiments done that showed that we can get much lower injection radii where we have a stable system than what is actually determined theoretically. So this is not good news for me But on the other hand, it really does make things more exciting. If everything matched up and it looked great, well, there wouldn't be much to do afterwards. So turns out there's a lot to do, because it seems like our theory is greatly underestimating the critical radius forcibility. So what do we do about this? Well, xanthan gum is a water-based solution and silicone oil is an oil. So my first thought was, must be surface tension. Must be significant. So I redid the calculations, incorporating surface tension. We get a modified lambda k, we get this additional term here. You can see that for large mode numbers, it will become very large negatives, so it stabilizes large mode numbers. Am I running out of time? Perfect. So we've got this stabilizing term here. But what was really kind of interesting is that when I looked at the critical radii with surface tension included, to actually get any kind of reasonable agreement with the experiments, it needed to be about 10 times its actual value, which seems a bit odd. But what I can say is this isn't a mistake in my calculations. There are other studies that have actually mirrored this. Tomasina and her collaborators showed that with their experiments, they needed surface tension to be 7 times its value. So there's something weird going on, clearly. We're not quite sure what just yet. So it made me think maybe surface tension is not, what's causing this overestimation. So what I think is more likely is the effect of wall slip, which I haven't studied in a lot of detail. And why do I think it's important? Well, if you look at the top image, there seems to be a darker blue region near to the source, followed by a lighter region. And that means that the xanthan gum layer must be thicker where it's darker. So for that to happen, silicone oil, at least traces of it, must have been left behind as the xanthan gum was displacing it. So what happens is, even if tiny traces of silicone oil are left behind, that can act to separate the xanthan gum from the cell walls and greatly reduce the shear. So just as an example, if you have a purely extensional stress-dominated flow, that's if the walls were perfectly lubricated by the silicone oil, you would actually get viscosity measurements that are much larger. And in this case, instead of overestimating the critical radius, it actually seems that we now go the other way, we go too far. I guess another thing that really points the direction of wall slip being important is at the end of an experiment, once you stop pumping your xanthan gum and you just leave it for a bit, you actually get these really nice patterns forming. I think these are some other kind of vertical instabilities, but what this does suggest is there was something trapped in the xanthan gum. So presume that must be the silicone oil, since those are the two fluids that we're looking at. So there are further avenues to look at, but I think in this case it would be a good idea to try reduce wall slip in the experiments before going any further. So just to summarize, we looked at a model of the radial injection of a shear-thinning fluid to displace a viscous Newtonian fluid. The model, which was nice, led to really simple theoretical expressions, and we could easily compare that to experimental data. But those very basic comparisons, they did not match up. So there is really no point in going further at this stage until we either look at a different adjusted model or a better experimental setup, which is where I'm heading at the moment. Neglecting surface tension and wall slip, they might be the offending assumptions. I'm not giving up on the case that perhaps the way in which surface tension has been incorporated into the model, it might be too primitive. So perhaps there is something there as well. So I'm not necessarily ruling it out. And thank you for listening.